Okay, hello, I'm Michael, and my project for this course is a supervised learning regression on property prices of the city I live in called Bellingham. And so, taking a step back, a little bit of the structure of this video, go over the problem, the data set, cleaning it, getting it ready for modeling, exploratory data analysis, feature engineering, the modeling, model optimization, results and analysis, and discussions with conclusions. And so in this problem, or in this project, what I did is I wanted to predict home prices in the city I live in, Bellingham. So this is a regression task. And the data set or the motivation I used was hopefully to help real estate investors or property owners looking to buy property at a fair market value or looking to sell property at fair market value, or investors hoping they can handicap the market and make data-informed decisions. And so, key business questions I have right here: which property features are most predictive of property of market value? How accurate can we predict market value? And then, is there any insights? Like, can we analyze the features that help us determine, which help us determine the price? And so the data set overview, I grabbed this from PropStream, and overall it has 7,000 rows with 51 columns, and the target variable that we want to predict is the MLS amount. And so this is the sale price that the home eventually sells for. And so again, the property type, this is supervised learning, and it's a regression task. I put this in a data frame, we'll get into which columns are available, but in general, these are typical values for a property. So bedrooms, bathrooms, square footage. What's really cool is we're doing location within the city. And so we'll do some neat feature engineering. Success metrics, or in my models, I'm optimizing for the root mean square, so accuracy in dollar terms. But we also look at the R squared mean absolute error and the mean absolute percent error. I mentioned the motivation for this is really to get insight. People might be familiar with different models such as Redfin, Realtor.com, Homes.com, or Zillow, and you have the Zestimate. And I hope to have my own prediction with a breakdown of what are the key attributes. So jumping in, we have imports, kind of a typical standard machine learning libraries. For data and cleaning, what we really wanted to do, the objective is to initially this has 51 columns, lots of columns that I'm not interested in or that are not intuitively predictive of home prices. And so we're going to remove some of the personal identification information. We're going to standardize data types, handle missing values, um, and do some quick visuals. And so loading the data. Looking at the schema overview, here you can see all the columns that are available and then the missing values. And so a lot of these columns are missing all values available. And so we're going to drop a lot of those and handle the missing values. So let's see, I go through all that. And the conclusion here is that initially we started with 7,000 rows. We removed 358. We dropped 41 columns. And then what's remaining is kind of a clean form ready to get into feature engineering or getting ready into EDA, exploratory data analysis. Looking at zip codes. Oh yeah, before getting into EDA, I wanted to remove outliers. And so I did a IQR method where we are looking at the first quartile and then removing 1.5 beyond that, times beyond that, and then the third quartile and removing 1.5 times IQR beyond that. And so what you can see here in the graphs is the before and then the after applying the outlier detection, kind of the filtering method. And so you can see before and after. Before, there's quite a bit of outliers, and then we clean it up. In large part, in this modeling, what I wanted to focus on was not modeling kind of the extreme cases. I wanted to model just like your typical standard house in Bellingham. And so that's why I was very comfortable getting rid of some of the more exotic, kind of these outlier properties. We removed duplicate addresses. You can see there's only two duplicates. And so going into exploratory data analysis, you can see we initially started with 7,000 rows. Now we're down at 5,200, down to 13 columns. We handled missing values, filtered out extreme outliers, and ensured each property address is unique by dropping the duplicate listings. So an EDA kind of did a laundry list of items. We're looking at summary statistics, histograms, correlation heat maps, different price distribution, statistical test, pairwise relationships, on and on. And then we get into the key insights, which I'll go quickly through those. But just starting at the kind of off the first thing you want to ask is what are the summary statistics of our data. And so we have our sale price, the MLS amount, looking at 584,000. And then as a sanity check, you're seeing, okay, the average home is 3.2 bedrooms and about two bathrooms. So it's a 3.2, and then it's 1,869 square feet, which are numbers I would expect living in this area and knowing some about the housing market here. Going through, looking at the outliers, which we already handled, looking at histograms of the different features. I'm going to kind of scroll through this, though. I don't want to take up too much time. And I'm just going to, well, I guess we go through, um, what is it? Some of the group price distributions. We're looking at bedrooms, bathrooms, um, and their respective MLS amount that they sell for. Statistical tests, we're looking at do mean prices differ by bedrooms and do newer homes sell for more than older homes? And you can see our ANOVA test, super low p-value. So absolutely uh, bedrooms determine, or if a home has a different bedroom, then it has a different price associated with it. Then our Welsh T test, similarly, newer homes sell differently than older homes in extremely low p-value. So we would accept that hypothesis. We would accept the hypothesis that this has a impact. Couple of pairwise relationships. So price, the MLS amount price is on the y-axis, looking at square footage, the lot size, and then the effective year built. They all have positive correlations. Looked at log transformations, but what I really want to spend time on is the correlation heat map. And so what I focused on is correlation with the MLS amount. This is the price. Scrolling down beyond the graphic, we see top correlations as the building square footage, the bedrooms, the bathrooms, and the lot square footage. And then those are exactly what you would expect it to be. And so key takeaways, size matters most, bathroom and bedroom matter a lot, and location right now is weaker, but we'll do some feature engineering on that. Speaking of feature engineering, overall did a lot here. And so I won't go into everything, but we're looking at different ratios, log transformations, seasonality of the market. Maybe prices are higher in the summer or winter or fall, spring, different interactions. And then the second set, we're looking at the geo features, such as proximity to the highway, proximity to the university, downtown, on and on. Um, and so I create all those features, scrolling through those. We get to our new heat map with all the new features. Um, and so this one, you can't really read it, but what I did is instead I took the top 30. And so you see the big one is days since sold. So kind of when it sold is very important, the square footage, and then several of these efficiencies, ones that we had made. Um, so the feature engineering, what we added, scale and age, efficiency ratios, geoproximity, um, top correlations. I mentioned time recency, size, intensity, and efficiency. Um, and so I guess before we get into modeling, I think there's this obvious note, we have a ton of features, so we're going to expect a lot of multi-collinearity among these variables. And so we're probably going to want regularized models such as Ridge, Lasso, and Elastic Net. Um, and so for modeling, what I did is I first modeled without the features, kind of on the raw data. And I think what I'm thinking is that's going to be our baseline. And then on the feature engineering, we'll run similar models and we'll be able, kind of exciting to see, hey, here's the raw here's the model output, model results, performance with the raw, and then feature engineering. And then down below, we'll do a final optimization, take the best model, do a grid search, cross-validation, and all that. So this, I'm going to kind of scroll through. We have a lot of helper functions, get into some visualizations. And then here we get to the our final results. And so the model performance summary, which we're looking at the model, the R squared on the training, the R squared on the test set, the RMSE on the test, the mean absolute error on the test, and then the test mean absolute percent error. And so starting at the bottom, which we're only doing the raw features I had mentioned, you can see our RMSE is about 164, 155,000 for linear and XGBoost. And so this was quite bad. This had a mean average percent error of like 30 and 27%. But as we went to the featured engineering and the different models that would handle collinearity as well as nonlinear interactions, you can see we went from about 27% average percent error up to 17% average percent error. And then XGBoost performed the best. And then we did a randomized grid search with cross-validation, 50 different iterations to improve the hyperparameters. And our final model came out, our best model, test RMSE, mean average error, and then mean average percent error of 13%. And for each of these, or here's the grid search, you can see the what parameters were tested, which hyperparameters for XGBoost were tested. You could see which features had the top importance, such as, recency, when it was last sold, a large house flag, the sector within the city, helped determine its price. And then we were looking at mainly the residuals, the QQ plot, residual histogram, for each of these models I had done. And so um, that's the conclusion. So we had XGBoost, our let's see here, XGBoost mean average percent error of 13%. Our discussion and conclusion, key takeaways. Feature engineering was very important. Um, Before feature engineering, we had a 30. I guess we were 30% mean average percent error, so we were 70% accurate. And then with feature engineering, we boosted from 70 all the way up to 87. So with a 13% mean average percent error. Um, we saw hyperparameter tuning on that final model. It helped marginally. Feature engineering was definitely more important. Another big one we saw was that nonlinear models outperformed the linear models. And so I had done random forest and XGBoost, and all of those had superior performance to the linear models, such as Ridge, Lasso, and ElasticNet. So what did not work well, taking a step back again, was linear models and the raw features alone. And then for future work, I think there's a lot of room on doing a similarity search on like, hey, this home that you're interested in is most similar to these other homes. I think there's room on fe the feature engineering side as well for marginal gains. You could probably do an ensembling method where you're looking at multiple models and then getting a prediction. And then adding temporal rolling features such as, hey, when this home is listed for sale, what's the average price in Bellingham? And so that's the end of this presentation and end of my modeling for price prediction real estate in Bellingham, Washington. And thank you so much for watching.